All right, question 9 says compute the flux of the radial field F, which is k times the position vector r divided by its magnitude cubed across the sphere of radius a centered at the origin. The sphere is oriented so that normal vectors point outward. All right, so this is the radial field we've now spent a fair amount of time with. This is the field that satisfies the inverse square law. And we also saw in the last section that its divergence is equal to 0 as well as the curl, right? It's the zero, the curl is the 0 vector. So in other words, it's source free and irrotational on its domain, which is all of R3 excluding the origin. And so with the orientation here chosen so that the normal vectors point outward, given that this is a radial field here, the field vectors you see here in yellow are going to be parallel to those normal vectors to the sphere. So we're observing positive flux. Okay, so that's one thing to note. Now we're integrating over the sphere. So here's the parameterization for the sphere from the worksheet. Okay, so taking the whole sphere, so u, which is just the angle phi in spherical coordinates, varies from 0 to pi, and v varies from 0 to 2 pi. Here's the normal vector, tu cross tv, again, just straight from the worksheet. And we note here that this vector, tu cross tv, this points outward as well. So in other words, our parameterization is consistent with this chosen orientation for normal vectors to point outward. Okay, so if it were the case that the orientation was chosen so that the normal vectors pointed inward, then instead of using this vector, we would just use its opposite in computing the flux integral. All right, so now let's go ahead and set up that integral. Okay, so I have f of r of uv, which is just k over r cubed. See, if we're on the sphere of radius a, our radial distance from the origin is just constant a. So this denominator just becomes a cubed. And here, this is just the position vector on the sphere. Now I could just copy this blue vector right here and paste it over here. But for the moment, I'm just going to leave this as r of uv because as we'll see here in a few moments, some nice simplification is going to happen. All right, so here's what we need to compute, right, for the surface integral. We need to compute the dot product of f evaluated along the sphere with the normal vector tu cross tv. Okay, so I could again just as well punch in this blue vector here and this red vector here, take their dot product, and I'm going to get a fairly messy expression involving a lot of sine squareds and cosine squareds. But by doing some rearranging and using the Pythagorean identity for sines and cosines, all right, I could see that that thing will simplify a ton. But there's actually an easier way here. If you just notice that this vector sine u cos v, sine u sine v, and cos u show up in both of these expressions, right? So if I look at the position vector r, okay, I get this vector, which I'll call w, sine u cos v, sine u sine v, cos u. That's just multiplied by a here to get the vector r, okay? And then likewise for tu cross tv, see, there's that vector w, and then I just have this factor of a squared sine u out front. What this vector w is just the unit vector in the direction of our position vector on the sphere. So this thing lives on the sphere of radius 1. So its magnitude is 1. And then I just note here that r of uv is just a times this vector. And this cross product vector, tu cross tv, is just a squared sine u times this vector w. Okay, so now to take this dot product, if I incorporate this vector w, it can simplify things quite a bit. Okay, so I get k over a cubed times r, which is just aw, dotted with the normal vector tu cross tv, and that's just a squared sine u w. And see here I'm going to get a w dotted with itself, which is just the square of the magnitude of w, but since w lives on the unit sphere, that magnitude squared is just equal to 1. And notice here I get an a times a squared, so that's a cubed, and that's going to cancel out this a cubed. So I'm just going to get a k and a sine u left over. And we're integrating from 0 to pi for u and from 0 to 2 pi for dv, so when all is said and done, you get an integral of 4 pi k. Okay, so again, it's certainly not wrong to just punch in these expressions for f evaluated along the sphere and this normal vector here, tu cross tv, but this kind of thing greatly simplifies the calculation. So be looking out for that kind of thing. All right, well, that is going to do it. Thanks so much.